We're going to look now at graphing the solution of a quadratic inequality. Now when we're looking at the graph of a quadratic inequality and we want to find the solution set, we want all the values of x that will make this inequality true. Now when it's quadratic, it's a little bit more difficult to find that solution set than it is when it's a linear inequality, but still not so bad. The thing that we have to do in terms of the quadratic inequalities is to kind of look at what we would have done when we were looking at solving quadratic equations by factoring, but then find the portions on the line that has all of those values of x that make the inequality true. So the first thing we're going to do here is we're going to subtract 6 from both sides so that we have our quadratic expression and our inequality and 0 on the other side. And the reason we're doing this is that 0 is the cutoff between numbers that are positive and negative, and it will be much easier for us to evaluate whether this expression is positive or negative if we write it as a product. And we can come in at the solution set to the original inequality that way. So next what we're going to do is factor this quadratic expression, and it's in descending order. There's no common factors. It is a trinomial with the lead coefficient of 1. So I'm looking for the factors of -6 that add to get -1. Those factors are -3 and +2. So we will factor x squared minus x minus 6 as x minus 3 times x plus 2, and that's less than or equal to 0. Now, I know from the zero factor theorem that if x is equal to 3, then this gives me 3 minus 3, or 0 times whatever that is, would give me a 0 out for that product. If x is equal to -2, -2 plus 2 is 0, and 0 times whatever this number would give me 0 as a product. So I know that I have these two multiplied together would give me a product of 0 if I had an x value of -3, or sorry, an x value of 3 or an x value of -2. And that gives me kind of a setup of where we might have transition points between the x values that make the original inequality true and those that don't. So what we're going to do next is to think about what we would have had with setting each of these factors equal to 0, adding the 3 over, I have x equals 3. Subtracting the 2 over, I have x equal -2. And since these are the places where my product came out exactly to be 0, like we discussed before, I want to mark those on my number line. So x equals 3, we'll put 0 here, 1, 2, 3. And x equals -2 lies there on the number line. And they're kind of possibilities of places where we might have a transition happening. When we look at the original inequality, it says or equal to 0. And or equal to 0 means it's okay if the product comes out to be 0. So I know I'm going to include these cutoffs in our solution set once we find out which way the shading goes for where the values of x that make it true are. And then with those cutoffs, we are going to just test values of x within the different spans that these cutoffs make on the number line. So I have a span of x's down here, a span of x's between -2 and 3, and then a span of x is bigger than 3 that we want to test. So pick any number left of your leftmost cutoff value. So let's pick, for example, -3 as a test. Well, if I put -3 into the factored form and this inequality, -3 subtract 3 is -6, and -3 plus 2 is -1, and -6 times -1 is a +6. Now, +6 is not a number that's less than or equal to 0, so I know that this is not a region that has values of x that make that inequality true. Now let's test an x value that's in the next span, the values of x between -2 and 3. Let's test x equals 0. Well, 0 minus 3 is -3. 0 plus 2 is +2. and negative 3 times positive 2 is a negative 6. And negative 6 is a number that's less than or equal to 0, so that works. So every number in that span will also work. So we'll shade that to say that that looked good. And then we're going to test a number bigger than our biggest cutoff. So a number bigger than 3, let's test x equal 4. Because that's a number bigger than 3. Well, 4 subtract 3 is 1. 4 plus 2 is 6. 1 times 6 is 6, which is not less than or equal to 0. So that part doesn't work either. So I have the span of x's that make that inequality true are any x value from negative 2 to 3. And because I'm supposed to include my cutoff, because I had the or equal to 0 in this, I will put a bracket at negative 2. And I'm supposed to also include 3, so I'll put a bracket at 3. So the graph of the solution of that inequality is from negative 2 including negative 2 all the way up until you get to and include 3. Now another thing the problem may ask you is to write the interval notation for this solution. And if I want to write the interval notation you want to go from smallest to biggest, and you want to write with writing down the number that is the smallest within the solution set that you want to represent. So that's negative 2, then comma up to the biggest number is 3. And then at those endpoints of your interval, you want to put the symbol that represents whether you're supposed to include the endpoint or not. And in this problem, we are. So we'll put a bracket at the negative 2, and we'll put a bracket at the 3. So this interval notation represents all the real numbers that are starting and including negative 2 all the way up until you get and including 3, which is the solution set also of our original quadratic inequality.